disjoint set or union find. What are disjoint sets? Disjoint sets are sets that do not have any element in common. That is, if there is a set A and another set B and they have a lot of elements in each other, but there is not even a single element which is common to both A and B. This is when you say A and B are disjoint sets. You may be having a doubt now. Why are we discussing these things in the data structures lecture? The reason is what we are discussing here is a data structure called disjoint set. And this data structure, the disjoint set data structure, is used specifically to manage a collection of disjoint sets, right? So this is why we are going to discuss in detail about this particular data structure. This data structure is used only for managing disjoint sets. Whatever be the number of disjoint sets you have, you can easily manage all those using this disjoint set data structure. First of all, you may also have noticed that I wrote here as union find. Why is it called as union find? The reason is disjoint set data structure supports two primary operations. First one is find operation and the second one is union operation. So because the two primary operations on this data structure are union and find, that is why we also call it as union find data structure. Okay. So first let us understand how do we represent any particular element in disjoint set data structure, and then we'll go to the operations that are performed on them. First thing is, how do you represent any element in disjoint set data structure? Each set is represented as a tree. So generally you have a tree like this. Trees you already know about. If you have a tree, each set in a disjoint set data structure is a tree. So let us say you have 2 or 3 disjoint sets. Then each disjoint set will be represented by a separate tree. But generally in any tree, you will have parent pointing to both its children. That is, you will have a left child and a right child. This is how you generally use pointers in trees. But in case of disjoint set data structure, all the children are going to have a pointer towards the parent. So whatever you learned in tree lectures, the pointer is going to be directly opposite to that. Initially, it used to be from parent to the child, but this time in disjoint set, the pointer will be from child to the parent. So every single child will be having a pointer to the parent. This is how disjoint set data structure is made. And what about the parent? Parent will be having a pointer to itself. So this is the structure of a disjoint set. So the root of the tree, which is whichever be the root of the tree, that is called the representative of the set. Each set will be represented by a representative. Why do you want this? Because you are having a lot of sets. How will you say this set is some particular set? There should be some name or something by which you can address any particular set. So that name is the representative element. You would say this is the set represented by this particular element. So how do you identify the representative element? That element will be having a pointer to itself. Every other element will be having a pointer to its parent. So we are somehow considering that the parent of the representative element is that element itself, right? So next thing is, what are the operations on it? One is find operation and the other is union operation. What is a find operation? Find operation is used to determine which set a particular element belongs to. So if you want to say which set, how will you say? You will say which is the representative element of the set. So basically, this find operation is going to find out which is the representative element of the set. How will you find it out? Wherever you be standing, what should you do? You should keep traversing till the point you reach the root. How do you know you reach the root? Whenever you reach the root, it will point to itself. So whenever you see that there is a node for which the parent is that node itself, you know you reach the root. So you have to traverse till you reach the representative element and you will return the representative element. This is the find operation. What about the union operation? Union operation, it is supposed to merge two sets into a single set. Let us say you want to merge this set and make it a single set. Whenever you want to do this, you call the union operation. And how is union operation done? First thing is, as part of this union operation, you have to perform two different find operations. That is, let us say I want to take union of this particular node and this particular node. What will I do? First, I will do find of this node so as to find the representative element of that set. Similarly, with the second node as well, that is the second node of which I want to take union, I will do find operation so as to find out the representative element of the set. At this point, I have the representative element of the first set and also representative element of the second set. Now, if I want to take the union, I can either make the representative element of the first set point to the representative element of the second one. This is one way. Otherwise, what can I do? I can take the representative element of the second set and make it point to the first one. So basically, I'm considering it as the child of the other one. So you are free to do whichever you want. In the later lectures, we'll see special techniques which will increase the efficiency, and for that there are specific rules to be followed. For now, in union find operation, you can arbitrarily choose any of these sets, right? Let us take example and understand exactly how these operations are done in a disjoint set data structure. Okay. And one more thing, you may have doubt on how we are going to store this structure. Generally, if you have a tree, how will you store it? You will have a data node and then you will have a left pointer and a right pointer. And what will you do? You will have a, let us say, a structure, and in the structure you will have these particular data types. But instead, in order to represent a disjoint set, there is an easier method. You don't have to actually form structures and then see for the pointers and all. Instead, you can easily manage it with a single array. You just want one array, and this array is called parent array. Parent array. What is the importance of parent array? Corresponding to each of the element in the sets, whichever be the set, for all the element, there will be one entry in this parent array. What will it say? It will say whichever is the parent node of that particular node. Now think back. If you want to do find operation or union operation, the only information you want is the information of parent. You just want to know who is the parent of this node, and that information is easily available from the single array. So you don't want any complex implementation of this. With a simple parent array, you can manage union find data structure. Let us see an example. So it will be very clear for you. It is very easy to manage union find. So once you see it, you will understand it. With a single array, we'll easily manage this data structure. Let us first have a parent array. This is my parent array. Initially, my parent array will be empty. This parent array. These are my elements. So here I am drawing so that you get a pictorial view of what I'm going to do. Just for that purpose, I'm drawing it here. Let us say my first element is 0. Initially, each element will be its own set. So there will be no two elements in a set. Instead, each element will be its own separate set. So 0 is one element. It is pointing to itself. Why is it pointing to itself? Because in this set, only element is 0. 0 is the root. It is the representative element. Whichever is the representative element will be pointing to itself. So 0 is then I have 1. This is the second node. This is also its own set. Then I have 2. 2 is also its own set. What about 3? This is another set. And let us say I have one more, 4 as well. These 5 sets are there as of now. Each set is containing only one node. This is the starting position. What should I have then? I should have 5 entries in the array. 1, 2, 3, 4 and 5. I'll have 5 entries in my array. What will I have here? Each entry is corresponding to each of these. This will be 1. Oh, sorry, I have from 0, right? 0, 1, 2, 3 and 4. At the initial position, what are the parents? Each element is a parent of itself. So I know the parent of 0 is 0 itself, parent of 1 is 1, parent of 2 is 2, parent of 3 is 3 and parent of 4 is 4. This is the starting position. What should I do now? Let us say I want to do union of 0 and 1. This is the operation that I want to perform. How will I do union of 0 and 1? First I will go to 0, then I will go to 1. For each of these, I have to do a find operation so as to find out the representative element. So I'll initially do find of 0 and I'll see that how will I do find? I will keep traversing upwards till I reach the representative element. So I'll see what is the parent of 0. What is the parent of 0 here? Parent of 0 is 0 itself. So whenever parent is that element itself, that means it is a representative element. So find of 0, answer is 0. Similarly, if I do find of 1, I will get as 1 itself, which means at this point, I have a representative element of both the sets. Once I have representative elements, how can I do the union? I have to make one representative element the child of the other. So here the choice is arbitrary. I can do whatever I want. I can either make 0 as the child of 1 or I can make 1 as the child of 0. So anything can be done. So let us keep 1 as the parent. Okay. 1 is the parent and I have 0 as the child. So 0 will now point to 1 and 1 is pointing to itself. So how do we update this in the parent array? Here I just showed it in illustration. Ideally, all these changes while you are writing a program or something, you will be making all the changes in this array only. From the parent array only, you are going to do all the manipulations. What change will happen here? You are going to change the parent of 0 to 1. Just with this single change, you performed union operation. So single change means initially you did find operation as well. That is also directly from array. You just checked who is the parent of that node. Whenever you found that the parent is that node itself, you understood it as the representative. So two find operations and then a parent change operation gave you the union. So at this point you did union of 0, 1. Let us say union of 2, 3. This is what you want to do next. How will you do this? 2 and 3. Again, if you do find operation, if you do find of 2, you will get 2 itself because 2's parent is 2. Then you will get find of 3. 3's parent is 3 itself, which means find of 3 will give you 3. What is the next step? Once you found both the representative elements, you can make one point to the other. So either you can make 2 point to 3 or 3 point to 2. So let us say we'll make 3 point to 2. So 2 is the parent now and you have 3 as the child. So 3 will be pointing to 2, 2 will be pointing to itself. And what is the change in the parent array? 2's parent will be 2 itself, but 3's parent you have to alter to 2. This is the change that you make. So in order to make it look like this, while programming, the only change you have to make is this single entry in the array, right? The parent of 3 has to be changed from 3 to 2 and you can imagine that you are having this structure, okay? Let us say we want to do union of 3, 4 now. So the reason I'm doing all these operations is in the next lecture, when we do union by rank and then later path compression, you should be able to relate all those with whatever we are doing here, okay? I want you to understand how the algorithm will improve when we apply union by rank in the next lecture. Okay, so that is why I am doing all this union operation. Just listen to this. So union 3 4, 3 is this, 4 is this. I'll do a bit faster now. Find of 3 will give you 2. How did you get that? Parent of 3 is 2. Then I'll do find of 4. Find of 4 will give me 4 itself. Why is it? Parent of 4 is 4. What will I do now? I got representative element of one set, representative of other set. Both the representatives are ready. I can make one point to the other. So let us say I will make 2 point to 4. How will I do that? 4 is here. I will make this 2 point to 4. Let us say it is here. 3 is here. 3 will point to 2, 2 will point to 4, 4 will point to itself. This is my present situation. Let us do one more union so as to make everything together. Let us say union 0, 2. So find of 0. What is find of 0? One more thing. Here when I did this, I have to make that change in the array. What change I have to make? Parent of 4 is 4 itself. Parent of 2 is 4. So this I have to change to 4, right? This is the change that I have to make. Parent of 3 is 2 itself. There is no change. Only one change is to be made in the parent array in order to apply the union operation. Okay. So now I am going to do union of 0, 2. Find of 0 will give you 1 because 1 is the parent. Again, when you do 1, you know 1 is the parent of itself. That is how you stop the find operation. Find of 2 will tell you parent of 2 is 4. Then you will go to 4. Then you see parent of 4 is 4 itself, which means 4 is the representative element. So find of 2 will give you 4. So you know the representative elements are 1 and 4. What will you do? You will make any one point to the other. So let us say we will make 4 point to 1. So how will you do this? You will have 4 here, you have 2 and you have 3. So 3 will point to 2, 2 will point to 4, 4 will point to 1. And ideally in program, how do you make this change? You make that change in this array. 4 is what you want to make it point to 1. So parent of 4 is updated to 1. It's as simple as that. Just one updation and this complete change is done. So this is why I told that instead of maintaining a separate structure and node, it is much easier with this parent array in disjoint set data structure. This is how you are doing union operation. Let us just do one find operation as well, just to understand. Find of, let us say 3. What will happen? From this 3, this is not there now. From this 3, you will traverse up, up, up till 1. How will you do that? You will see parent of 3 is 2. Then you will see parent of 2 is 4. Parent of 4 is 1. Then you will see parent of 1 is 1 itself, which means 1 is the representative element. So you got find of 3 is 1. This is how you do find and union operations in a disjoint set data structure. Here we didn't apply any additional algorithms that are required, additional techniques that are required. There is something called union by rank and there is something called path compression. In the next 2 lectures, we'll see about this. As of now, at this position, let us see what are the time complexities of find and union operations. Let us say you want to do find operation. In find operation, what are you doing? In the worst case, what will happen? You may have to travel from the bottom of the tree till the top of the tree. And in the worst case, this tree may look like a linked list. It may simply like one to the next, that to the next, that to the next, and so on till the representative element. In that case, if there are a total of n elements, you may have to go from the last element till the first element. So if there are n elements, then your find operation will take, in the worst case, order of n time. So this is the time complexity of your find operation. This will improve as we go to the next lectures. For now, understand it is order of n. So when will this happen? When the tree is looking like a long chain. This is when this worst case happens. What about the union operations? Union operation has 3 major steps to be done. 1 is a find operation on the first set. 2 is again a find operation on the second set. And then there is an order of 1 operation to make the representative of 1 as the parent of other. That order of one operation is just to alter the parent in the array. But the problem is two find operations which are time taking. So both of these will take order of n time each, and because of which your union operation will also take order of n time. So the time complexity for find operation is order of n, union is also order of n. In the next lecture, we'll see how we'll apply union by rank and then we'll decrease the time complexity. Then the lecture after that, we'll apply path compression and then again we'll improve time complexity. Finally, we'll reach a constant time. That is what we are going to get to. Disjoint set data structure, both find and union operation, you will be able to do in constant time. Okay.